Hello, my name is Brianna Kessler, and this is my presentation on the fertigation for blueberry production in Florida. I was advised by Dr. Guodong David Leo, and here I have the EDIS article IDs that I used to compile this presentation. I hope you enjoy. First, I'll start with talking about Florida's commercial blueberry production. Florida's commercial blueberry industry has expanded in acreage and value. Based on statistics, about 1,000 acres of commercial blueberry production in 1993 developed into more than 5,100 acres in 2019, from 39 million in 2007 to 62 million in 2019, based on USDA-NOS in 2019. Consumption of blueberries per capita has increased exponentially by 400% during the last decade, according to Braswell in 2010. Approximately 24.2 million pounds of blueberries were produced in Florida in the 2019 season. Yet, Florida only contributed 4.4% of total U.S. fresh blueberry production. This was more than 565.5 million pounds. Additionally, the value of blueberries destined for processing has increased. The total U.S. value of processed blueberries has grown from 62.3 million in 2009 to 908.7 million in 2010. The most recent consensus was completed in 2021. The U.S. commercial blueberry industry value of production was 1.1 billion on 102,400 acres. In 2021, U.S. blueberry growers harvested 774.1 million pounds of blueberries, leading the world in total volume of blueberry production. Georgia, North Carolina, and Florida were among the 8 producing states with 20,600 acres, 7,400 acres, and 5,700 acres harvested, representing 1/3 of all U.S. blueberry acreage in 2022, based on studies from the USDA in 2022. Now I'll go ahead and talk about Florida's blueberry market. Early blueberry production is possible because of Florida's subtropical climate and has been a profitable marketing window. The Florida blueberry market is expected to experience further growth and expansion. Fertigation is recommended for commercial blueberry production because it is proven to increase nutrient and water use efficiencies and reduce nutrient leaching and environmental concerns. In fact, successful fertigation can enhance sustainability and maximize profitability for commercial blueberry production. A key factor in fertigation is the correct calculation of fertilizer injection rate and time for the acreage. Drip irrigation for blueberry production. Fertigation can be practiced via drip irrigation or other irrigation systems, such as sprinkler irrigation. However, drip irrigation is most used for blueberry production. Drip irrigation utilizes a network of valves, pipes, tubings, and emitters, which allows precise control of the application of water and fertilizer by releasing water to drip slowly near the plant's roots. Drip irrigation is considered a best management practice. The BMP program for vegetables grown in Florida is described in Water Quality/Quantity Best Management Practices for Florida Vegetable and Agronomic Crops. This was based on a study from the Florida Department of Agriculture and Consumer Services in 2005. Drip irrigation may not be a beneficial practice for all farms. However, when properly managed, it is a valuable production technique that may reduce labor and production costs while improving productivity. Small farmers should evaluate both the advantages and disadvantages to determine the benefits of drip irrigation for their operation. Now I will go into components of a drip irrigation system. Components include a water source, and you can use surface water such as pond, river, and creek water, groundwater, and potable water. Another component is a pumping system, which moves water from the water source to the field through the distribution system. You will also need a distribution system, which conveys the water from the source to the field. Another attribute you'll need is drip tape or drip tubes, which delivers water to each plant through a thin tube with regularly spaced small holes called emitters. You will also need injectors, which introduce fertilizers, chemicals, and maintenance products into the irrigation system. You'll need a filtration system, which removes large solid particles in suspension in the water. You'll also need system controls, which comprise of a multitude of items. System controls monitors systems performance, and these include pressure regulators, which regulate water pressure at a given flow, water meters, which monitor and record the amount of water moving through a pipe where the water meter is installed. You will need pressure gauges, which monitors water pressure in the system and ensures operating pressure remains close to the recommended benchmark values. You will need soil moisture measuring devices, which measures soil moisture in the root zone of the crop, and you'll also need electrical timers. These are used to automatically operate a drip system at preset starting and ending operating times of the day. Now I will go over the advantages of drip irrigation. Some of the advantages of drip irrigation include reduced water use, and drip irrigation only waters the plant's root zones. The drip typically requires 0.25 to 0.5 of the volume of water required by comparable overhead irrigation systems. Another advantage is joint management of irrigation and fertilization. This improves efficiency of water and fertilizer. Hence, fertilizer costs and soluble nutrient losses may be reduced. Another advantage is reduced pest problems. Weed and disease may be reduced because drip irrigation does not wet the row middles or the foliage of the crops. Another advantage is the simplicity. It is widely available in several diameters and easy to assemble. Another advantage is low pumping needs. The operating pressure, 20 to 25 psi at field entrance or 10-12 psi at the drip tape, compared to overhead systems from 50 to 80 psi. Another advantage is the automation. Drip irrigation may be simply managed and programmed with an AC or battery-powered controller. Another advantage is adaptation. Drip irrigation is adaptable to oddly shaped fields, thereby maximizing the use of available land. There are production advantages. Polyethylene mulch increases product cleanliness and reduces the risk of contamination with soil-borne pathogens. Reflective mulch reduces the incidence of viral diseases by affecting insect vectors such as thrips, whiteflies, or aphids. Now I'll go ahead and discuss the disadvantage of drip irrigation. Drip irrigation requires an economic investment. It typically costs $500 to $1,200 or more per acre. Part of the cost is capital investment, which is good for several years, and another part is due to the annual cost of disposable parts. Drip irrigation requires maintenance and high-quality water. The drip tape must be replaced if emitters are clogged or the tape is damaged. Another disadvantage is water application pattern must match the planting pattern. If emitter spacing is too far apart, it does not match the planting pattern, and root development may be restricted and or plants may die. Another disadvantage is safety. Tubing may be lifted by wind or displaced by animals unless it is covered by mulch or soil or fastened with wire anchor pins. Another disadvantage is leak repair. Drip lines can be easily cut or damaged by other farming operations, such as insects, rodents, or birds. Another disadvantage is disposal causes extra cleanup costs after harvest. Planning is needed for drip tape disposal, recycling, or reuse. Now I will discuss the calculation of injection rate and time for blueberry production. Fertigation rate and time depend on the irrigation water flow rate and fertilizer application rate. To keep the simplicity, we will use nitrogen fertilizer as a starting example. For other nutrients such as phosphorus and potassium, the principle is the same. For most cases, 0.1% of the irrigation flow rate is a proper injection rate. Based on the research study titled Nitrogen Uptake and Allocation at Different Growth Stages of Young Southern Highbush blueberry plants, the results stated about half of the nitrogen derived from the applied fertilizer was allocated to leaves at all labeling times except the early bloom stage in 2016. These results suggest that young southern highbush blueberry plants absorb greater amounts of nitrogen during summer and early fall than in spring. 6 steps are needed to calculate the injection rate and time for fertigation if a solution nitrogen fertilizer is used. Step 1. Determine the total amount of nitrogen needed for the fertigation event. Calculate the total amount of nitrogen needed. We will start by multiplying the farm size in acres by the nitrogen rate to be applied in pounds per acre. The linear bed feet can be used if you know your total linear feet of bed and the width of row spacing. For example, for a blueberry farm with a 4-foot bed center and 8-foot row spacing, the actual linear feet of bed per acre can be calculated as follows. 43,560 square feet per acre divided by 8 feet equals 5,445 linear feet of bed. Step 2. Calculate the total weight of liquid fertilizer needed for fertigation. The total weight depends on both the total nitrogen to be applied and the grade of the selected nitrogen fertilizer solution. For instance, urea ammonium nitrate solution 32-0-0 contains 32% nitrogen by weight. The total weight of the fertilizer solution to apply is equal to the total nitrogen needed from step 1, divided by the nitrogen concentration, 0.32 in this example. If you need 100 pounds of nitrogen for a particular fertigation event, how much UAN-32 do you need? Divide 100 pounds by 0.32. You will need 312.5 pounds of UAN-32. Based on the research study titled Optimizing Nitrogen Fertigation Rates for Young Southern Highbush Blueberries, the results were: the nitrogen rates did not significantly affect leaf nutrient concentrations. More excellent nitrogen rates advanced bloom and harvest. It increased percentage of ground cover, fruit yield, and berry numbers per plant, but decreased mean berry diameter and weight. Step 3. Calculate the number of gallons of liquid nitrogen fertilizer. This is determined by the density of liquid nitrogen fertilizer. Every solution fertilizer has a density listed on the fertilizer label. For example, 1 gallon of UAN-32 weighs 11.05 pounds. Thus, the density of this fertilizer is 11.05 pounds per gallon. The amount of fertilizer in gallons to apply is calculated by dividing the total weight of solution fertilizer from step 2 by the density. So you will take 312.5 pounds of UAN-32 from step 2 and divide by 11.05 pounds per gallon, which equals 28.28 gallons of liquid nitrogen fertilizer. Step 4. Calculate the dilution factor. The dilution factor is determined using the nitrogen concentration of the solution nitrogen fertilizer and the target nitrogen concentration in the irrigation water parts per million for the fertigation event. The fertilizer grade is 32% and should be first converted into ppm by multiplying it by 1 million. The fertilizer concentration in ppm, 320,000 ppm, is then divided by the target nitrogen concentration, which is 150 ppm. The result is the dilution factor, 2,133.33. Step 5. Calculate the injection rate. The injection rate is determined by dividing the irrigation water flow rate, which is 1,000 gallons per minute, by the dilution factor from step 4. So you will take 1,000 gallons per minute divided by 2,133.33, which equals 0.468 injection rate. Step 6. Calculate the injection time. The injection time is determined by dividing the number of gallons of solution nitrogen fertilizer needed from step 3 for the fertigation event by the injection rate from step 5. So you will take 28.28 gallons of liquid nitrogen fertilizer and divide that by 0.468, the injection rate, which equals 60.43 injection time. Here is a practical example. For this example, we will use UAN-32, which is 32% nitrogen and 11.05 pounds per gallon. We'll apply this to 5 pounds of nitrogen per acre to a 5-acre blueberry field with 8-foot spacing. The irrigation flow rate is 1,000 gallons per minute, and the target nitrogen concentration in the irrigation line is 150 ppm. To calculate the injection rate and time, we'll do step 1, find the total nitrogen. We'll take 5 pounds per acre of nitrogen and multiply that by 5 acres, and that'll get us 25 pounds of nitrogen. Step 2, we'll find the pounds of UAN-32 needed. So we'll take 25 pounds of nitrogen and divide it by 0.32, which is the percent of nitrogen in this bag of fertilizer, and we'll get 78.1 pounds of UAN-32. Step 3, we'll find the gallons of UAN-32 needed. So we'll take 78.1 pounds and divide that by 11.05 pounds per gallon, and we'll get 7 gallons. Step 2, we'll find the dilution factor. We'll take 0.32 and multiply that by 1 million ppm, and then divide that answer by 150 ppm, and that will get us 2,133.3. Step 5, we'll find the injection rate. We'll take 1,000 gallons per minute and divide that by 2,133.3, and that'll get us 0.47 gallons per minute. Step 6, we'll find the injection time. We'll take the 7 gallons and divide it by 0.47 gallons per minute, and that'll get us 15 minutes. Therefore, in this case, 7 gallons of UAN-32 are needed for the fertigation event. The best unit to express irrigation rates when drip irrigation is used. Drip irrigation volume should be expressed in gallons per 100 linear bed foot of drip tape. In some cases, drip irrigation volumes can be converted to and from water heights by considering the relative surface of the field under the plastic mulch. For example, the relative surface under plastic mulch of a 1-acre field with 30-inch wide beds of 4-foot centers is 62.5%. I got this by doing 2.5 feet divided by 4 times 100. Hence, if 0.5 acre inch needs to be applied to that field through a drip irrigation system, the total volume of water needed is 8,484 gallons. I got this by doing 27,150 divided by 2 times 0.625. Because in a 1-acre field with beds of 4-foot centers, there are 10,890 linear bed feet of plastic. The drip irrigation rate should be reported as 78 gallons per 100 feet. I got this by doing 8,484 divided by 108.9. If a drip tape with a 24-gallon to 100 feet per hour flow rate is used, it will take 3 hours and 15 minutes to apply this amount of water. I got this by doing 78 divided by 3, and it gets me 3.25 hours. Why does clogging occur in fertigation systems? Since fertigation is a combination of fertilization and irrigation, clogging issues can be traced back to either the water supply or injected fertilizer. The primary reason for clogging associated with water is poor water quality. Water quality includes the physical, chemical, and biological qualities of irrigation water. The physical properties of water is the irrigation water can have too many suspended solids, such as debris and tiny clay particles, which can plug irrigation lines and emitters. Chemical. This includes high pH and high concentrations of cations and/or anions in the irrigation water. Biological. Bacterial growth can cause clogging problems when the bacterial population is greater than 2,600 colony-forming units, CFU, per gallon. Why does clogging occur in fertigation systems? Fertilizers can cause clogging problems if they are incompatible with fertigation. Chemical reactions may occur after the fertilizers are injected into the irrigation system. Additional problems can arise regarding the temperature of the mixing water, the coagulation and secondary chemical reactions in the mixing tank, or failure to keep suspensions for several reasons. Now I'll go over fertilizer incompatibility. So for example, when mixed, calcium from calcium nitrate and phosphate from diammonium phosphate can form calcium phosphate, which is insoluble and precipitates out, clogging lines and emitters during fertigation. Another example is iron. Iron is an essential element for blueberry bushes. The bioavailable form of iron for blueberry uptake is ferrous iron, and it is water soluble. However, when ferrous iron is oxidized, it is made into ferric iron, which is insoluble and not bioavailable for blueberry uptake. Now I'll go over chemical reactions. Hydrolysis can occur. This happens when urea or a fertilizer containing urea, so for example UAN-32, is injected into the irrigation water. The reaction produces ammonia and carbon dioxide as a urease accelerated enzymatic equation. Another chemical reaction that can occur is dissociation. After the hydrolysis of urea, the two products, ammonia and carbon dioxide, dissociate in water immediately. The dissociation of ammonia generates hydroxyl ions and raises the pH to 9.3. Another chemical reaction that can occur is oxidation. The ferric iron species contributes to slime-like growth inside the fertigation system. And then we have precipitation. At this high pH, both calcium and magnesium are readily precipitated with carbonate or hydroxyl ions. All of these precipitations cause slime-like deposits and intensify clogging problems. How can clogging be reduced? Here I'll talk about a few ways to reduce clogging. One of the ways is filter the irrigation water. This removes debris, clay particles, and algae before they enter the fertigation system. Another way is to acidify the irrigation water. Acidifying water sources can minimize the oxidation of iron and manganese and reduce chemical precipitation between cation and anion nutrients. Acid must always be added to water, but water must never be put into acid. Urea sulfuric fertilizers, hydrochloric acid, or sulfuric acid may be most effective. For example, urea sulfuric, like N-furic products, nitrogen fertilizers can provide acidification and nutrients, including nitrogen and sulfur, etc., and lower water pH. Urea sulfuric fertilizers are not compatible with many compounds. Another way to reduce clogging is to chlorinate the irrigation water. To effectively prevent bacterial growth in irrigation water, chlorine may be injected continuously at low levels. Either liquid or gas chlorine can be used. Another way to reduce clogging is to ensure that injected nutrients are compatible. To test the compatibility of a fertilizer solution with different ingredients, the best way is to prepare a small quantity of the solution before mixing various fertilizers, solutions, and performing fertigation called a jar test. To perform a jar test, put some of the fertilizer solution into a jar of irrigation water and then carefully watch for any cloudiness for approximately 2 hours. If milkiness occurs, then the injection of the fertilizer solution will cause clogging problems. Now I will talk about converting liquid fertilizer to dry fertilizer. Some things to keep in mind. Dry fertilizer and its active ingredients in fertilization are both gravimetric, in other words, expressed as a weight per area. Liquid fertilizer and its active ingredients in fertilization are expressed on a volumetric basis, that is, as a volume per area. The key point for the conversion from liquid to dry fertilizer is the density of the liquid fertilizer. The greater the density of liquid fertilizer, the more active ingredient volume. However, the active ingredients of liquid fertilizer are not linearly proportional to the fertilizer's density. To avoid any errors, the conversion calculation from liquid to dry fertilizer must include the liquid fertilizer's density and active ingredient content. Now I will show you how to convert liquid fertilizer to dry fertilizer in fertigation for commercial vegetable and fruit crop production. To determine how many gallons of a particular liquid fertilizer are needed per acre, use the following equation. So, a pound per acre of nutrient times a gallon of fertilizer divided by the pounds of the nutrient equals the gallons of fertilizer per acre. This figure I would like to credit my advisor, Dr. Guodong Liu. For example, the UF IFAS recommendation for commercial tomato production in Florida is 200 pounds of nitrogen per acre. The injection rate would be 1.5 to 2.5 pounds per acre per day from 1 to 13 weeks after planting. This was found by Olson in 2012. For this example, assume 2 pounds per acre per day for a particular fertigation event and 10 acres to fertigate. Therefore, we need to use 20 pounds of nitrogen for the fertigation event. How many gallons of liquid fertilizer, Dr. Earth, are needed to supply 20 pounds of nitrogen to 10 acres? So, we will use Dr. Earth, which is 3-3-3 of liquid fertilizer, which has a fertilizer density of 10.56 pounds per gallon. We will take 20 pounds of nitrogen over 10 acres and multiply that by Dr. Earth divided by 3% nitrogen. This gets us 66.7 pounds of Dr. Earth per acre. Now we'll take that 66.7 pounds of Dr. Earth per acre and multiply that by a gallon of Dr. Earth divided by 10.56 pounds. This gets us 6.31 gallons of Dr. Earth per acre. Now we'll take 6.31 gallons of Dr. Earth per divided by acre and multiply that by the 10 acres. This gets us 63.1 gallons of Dr. Earth. I would like to credit Dr. Guodong Liu for these examples. Now I will talk about a research paper titled Optimizing Nitrogen Fertigation Rates for Young Southern Highbush Blueberries. This study was done by Yang Feng, Jeffrey Williamson, Rebecca Darnell, Yunkong Li, and Guodong Liu. 1-year-old emerald and farthing plants were fertilized with 32 nitrogen, 0 phosphorus, and 0 potassium through drip irrigation at 0, 42, 84, and 168 and 336 kilograms of nitrogen per hectare annual rates. The results? Nitrogen rates did not significantly affect leaf nutrient concentrations, but more excellent nitrogen rates advanced the bloom and harvest, increased percentage of ground cover, fruit yield, and berry numbers per plant, but decreased the mean berry diameter and weight. The soil nitrate results from both emerald and farthing revealed it had a significantly greater risk for nitrate leaching than the lower nitrogen treatments in spring. The effect of nitrogen rates on fruit quality varied with cultivar and harvest season. Now I will talk about another research study titled Nitrogen Uptake and Allocation at Different Growth Stages of Young Southern Highbush Blueberry Plants. This study was conducted by Yang Feng, Jeffrey Williamson, Rebecca Darnell, Yunkong Li, and Guodong Liu. The effect of plant growth stage on nitrogen uptake and allocation was studied with containerized 1-year-old Southern Highbush blueberries grown in pine bark amended soil. 5 emerald plants were each treated with 6 grams, 10% 15 nitrogen labeled NH4-2SO4 at each of 12 dates over 2 years. From August to October of both years, external nitrogen demand was the greatest, and plants absorbed more nitrogen during the 2-week chase period, about 0.53 grams per plant in year 1 and 0.67 grams per plant in year 2 than in chase periods earlier in the season. During March and April, nitrogen uptake was as low as 0.3 0.03 grams per plant per 2 weeks in year 1 and 0.21 grams per plant per 2 weeks in year 2. Nitrogen allocation to each of the tissues varied throughout the season. About half of the nitrogen derived from the applied fertilizer was allocated to leaves at all labeling times, except the early bloom stage in 2016. These results suggest that young southern highbush blueberry plants absorb greater amounts of nitrogen during summer and early fall than in spring. Here is the take-home message, a summary of what I've gone over. So, the Florida blueberry market is expected to experience further growth and expansion in the future. Fertigation is recommended for commercial blueberry production because it is proven to increase nutrient and water use efficiencies and reduce nutrient leaching and environmental concerns. Drip irrigation is most used for blueberry production. There are 6 steps that are needed to calculate the injection rate and time for fertigation if a solution nitrogen fertilizer is used. Clogging in fertigation systems is caused by 2 factors. One, water is of poor quality, and when fertilizers are incompatible with fertigation. I provided a guide to reduce clogging. I also provided a guide to convert liquid fertilizer to dry fertilizer. Based on the study titled Optimizing Nitrogen Fertigation Rates for Young Southern High Bush Blueberries, the optimal nitrogen rates positively affected the bloom, harvest, percentage of ground cover, fruit yield, and berry numbers per plant. However, it decreased the mean berry diameter and weight. The soil revealed it had a significantly greater risk for nitrate leaching than the lower nitrogen treatments. We can consider the findings to optimize blueberry production in Florida. Based on the study titled Nitrogen Uptake and Allocation at Different Growth Stages of Young Southern Highbush Blueberries plants, the nitrogen uptake in year 2 was better than in year 1. Additionally, about half of the nitrogen was held in the leaves, proving that nitrogen uptake is better in blueberry plants during summer and early fall. And with that, that concludes the end of my presentation. These are the references that I used to compile my data. I hope you learned something new, and thank you so much for following me through this.